We're going to look at what de Moivre's theorem is, and it's used to find powers of complex numbers. So we're going to connect to what we last did, which involved multiplication of complex numbers in polar form. And what we saw, if we have two complex numbers, Z1. Now last time we said r cis theta, but let's use both notations. So the magnitude of Z1 cis theta 1 and Z2 likewise for its modulus and argument. So previously we saw this, Z1 times Z2 is the product of the moduli, and that's times by cos I sine, and the argument there is the sum. We sum the arguments of the original complex numbers, and that's what we did previously. Now here's a way of, this isn't a proof, this is not a proof, but it is a way of generating de Moivre's theorem. So if we have these same two complex numbers as such, and we multiply them as we just said, and let's say it's a case where Z1 equals Z2, so they're the same complex number. So let's say if they're the same thing, let's just call, instead of worried about subscripts, let's just call it Z. So Z is the modulus of Z, cis theta for Z. And if we square that, if we square Z, we get the modulus of Z times the modulus of Z, cis theta plus theta. That would give, because modulus of Z is a real number, we have Z modulus squared, and cis theta plus theta is 2 theta. Now, there's the result. What about if we go for Z cubed? That would be the previous result. Alright, so the previous result was Z squared, and we multiply it by Z again, which you can see occurs on the next line, and what we get is, following our rule for multiplying complex numbers in polar form, we would have modulus of Z cubed, we'd have 2 theta plus theta for the arguments, which is 3 theta, so we would have Z modulus cubed cis 3 theta. Can you see a pattern building? And even though this is not a rigorous proof, it can be shown, and it follows that for rational numbers, we're going to look at positive rational numbers initially, so that can include anything that's integer over integer, okay, where A and B, so that's where A and B are integers, so that's what a rational number is. We're looking at positive ones at this point. We can generalize that, and Z to the n is the modulus of Z raised to the power n times n theta. Now, did you notice that when it was cubed it was 3 theta, when it was squared it was 2 theta? Okay, so that's essentially de Moivre's theorem. So basically this is de Moivre's theorem, a famous mathematician, very important one. A lot of people pronounce de Moivre's theorem in some very strange ways. Okay, it's not Moivre's theorem. That's awful. Don't say that. All right, it's de Moivre's theorem, and you need to sound a little bit European. Abraham de Moivre was French, and there's an early photograph of him. Okay, with an early mobile phone. No, it's he's lived in the 16 and 1700s. Very important mathematician, but yeah, that's a rendering. That's not a photograph. Sorry. So in general, complex number Z, if Z is given as in polar form, modulus Z times cis theta, where n is a positive rational number, we can say that Z to the power n is the modulus of Z to the n times cos n theta plus I sine n theta. abbreviated in cos I sine notation, CIS. Okay, and by the way, complex numbers follow certain index laws, like the four of them are there. And this last one, we're going to look at that. What about if we have a negative number? Now, we were saying positive rational numbers. Well, we can deal with negative ones by looking at this property here, which we'll do in just a minute. Okay, two examples now. Now we could do these technically by leaving them in Cartesian form. Cartesian form named after Descartes, another important French mathematician. So that would be René Descartes, who was a French mathematician before Moivre. So you could leave it in there, but when you get to these higher powers, you'd be looking ahead here, and if you're wondering what that hiss is in the background, it is pouring rain at the moment. I don't mind, I'm dry, and we need some rain. So z to the power 4, we'd have to be going 1 plus I to the power 4, which might not phase some, but it might phase others. And if we get increasingly larger powers, there's more work for us to do in terms of expanding that binomial. So the polar form in de Moivre's theorem certainly has its place. Okay, so let's have a look at this example here. So we've got z equals 1 plus I. So finding the modulus first, we have the square root of 1 squared plus 1 squared, and that's root 2. So now we need to find the argument theta. It's in the first quadrant, so this one's hunky-dory. We have 1 over 1, inverse tan of 1 over 1, which is inverse tan of 1, and we got 45 degrees or pi and 4 radians. Now, because radians are way cooler than degrees, I'm going for radians. Radians work better if you do things like calculus as well, so I'm going for radians, the more logical angular measure. So we've basically got, we can write our complex number as root 2 cos pi on 4 plus I sine pi on 4, or simply in abbreviated form as such. Now this is not new work, this part. So let's raise it to the power in part B here. So z to the 4 would be root 2 to the power 4 cis 4 times pi on 4 okay, so that would equal, that's 2 to the half times 4, so that's 2 to the 4 over 2 using index laws, and that'll be cis of pi, so that's 2 squared, which is 4 cos, now we need to expand it back out, so you could have left it in that form the whole time, cos pi plus I sine pi, so 4 outside of, now know your unit circle would be my advice here, you should know it, so cos of pi is negative 1, sine of pi is 0, and that's got an operator I on it there, okay, plus 0i. So lastly, z to the power 4 equals negative 4 plus 0i, but I'm just writing the negative 4. It says find 1 over z cubed, and your answer in trig form. I'm going to put mine in polar form. Basically the same. Alright, so z, 1 on z cubed, following the index laws, is z to the negative 3. So we have a value of n. Now we're going to see this works fine for negative indices or negative values of n. So that would mean that we've got our values above here for z in polar form. So we have root 2 to the negative 3 cis negative 3 times pi on 4 so on the modulus there, that negative index can be written as such. And tidying up the argument there, we've got negative 3 pi on 4. And so that is, you could put that in index form or just leave it in the surd form. I'm going to expand it, in fact. So you've got root 2 cubed is root 2 squared times root 2. Now root 2 squared is 2. So that'd be 2 times another root 2. So it's 1 over 2 root 2. Okay, and now we're going to expand this to cos negative 3 pi on 4 plus I sine of negative 3 pi over 4. Now, know your unit circle, as I say. We've got 1 over 2 root 2, which we may rationalise later on. Now, cos of negative 3 pi on 4, so negative 3 pi on 4 is going to be going in the clockwise direction with a pi on 4 acute angle left over there. So that's in quadrant 3 where tan is positive, cos is negative, so it's the same as the negative of, so let me put this up here, same as the negative of cos pi on 4. So we look at the acute angle there, pi on 4, neaten that up a little bit there, cosine negative there, and then we've got sine is also negative there, and so it's minus, again, I sine pi on 4, which is essentially the answer. You could, if this is optional, I didn't ask for this, if you want to put it in Cartesian form, you've got that there, and not rationalising this 1 over 2 root 2 yet, I might not even need to. So cos of pi on 4 is root 2 on 2, so it's going to be the negative of root 2 on 2. Okay, we multiply those fractions together, they'll cancel, and so we have negative 1/4, and y is 1 over 2 root 2, and it's negative as well. So sine of pi on 4, so it's negative. We could have taken the negative out too back in this line here. Could have factorised that negative out and it would have ended there. Same answers. Okay, and sine of pi on 4 is root 2 on 2, so it'll be negative root 2 on 2, so it's 1 on 2 root 2 times negative root 2 over 2, and again we've got a cancellation there, and we have negative 1/4. So optionally in that's z to negative 3 there, in Cartesian form would be negative 1/4 minus 1/4 I. Didn't ask for that, but I gave that. So there's some work on de Moivre's theorem, an easy one then a harder one, and it has its place in facilitating the raising of complex numbers to powers.